Welcome to the second series of Network Operation.
Hello? For Series 2, we want to introduce you to 1. Wireless networking. 2. Network architecture. 3. Segmentation. 4. Wide area networking. 5. Risk management. 6. Security and network design. And 7. Performance and recovery. So, for Series 2, I will start us off with the exploration of wireless computer networking. Today, we'll unravel how computers communicate without physical connections. Wireless computer networking, often simply referred to as wireless networking, is a technology that enables computers, smartphones, tablets, and other devices to communicate with each other and access the internet without the need for physical wired connections. Instead of using cables, wireless networking utilizes radio waves, microwave signals, or infrared light to transmit data between devices. Wireless networking, or Wi-Fi, connects devices through radio waves. This technology eliminates the need for cluttered wires and cables. Radio frequency. Wireless transmissions utilize radio waves, which occupy specific frequency bands within the electromagnetic spectrum. Different wireless technologies operate within designated frequency ranges, such as 2.4 GHz and 5 GHz for Wi-Fi, and license bands for cellular networks.
The heart of this system is the wireless router directing data between devices. A wireless router serves as the central hub of a wireless network, allowing multiple devices to connect to the internet and communicate with each other wirelessly.
Network routing. Like a traditional wired router, a wireless router forwards data packets between devices on the local network, LAN, and between the local network and the wider internet. It uses a process called routing to determine the best path for data packets to reach their destination. The wireless router includes a built-in wireless access point, WAP, which broadcasts radio signals to enable wireless devices to connect to the network. These radio signals are typically based on Wi-Fi standards such as 802.11ac or 802.11ax and operate on specific frequency bands, for example, 2.4 GHz or 5 GHz.
Security is crucial in wireless networks. Protocols like WPA2 ensure that your data remains safe from unauthorized access. Wireless transmissions are susceptible to interception and eavesdropping, making security essential for protecting transmitted data. Encryption protocols like WPA2 and WPA3 are commonly used to secure wireless communications and prevent unauthorized access.
Speed and range are influenced by the router's specifications and the environment. Obstacles like walls can impact performance. The range of wireless transmissions defines the maximum distance over which devices can communicate reliably. Range depends on factors such as transmitter power, antenna characteristics, and environmental conditions, and it varies for different wireless technologies. Wireless networks support a variety of devices, from smartphones to smart fridges, tablets, laptops, desktop computers, smart TVs, gaming consoles, and IoT devices like smart thermostats and security cameras. Connectivity is more flexible than ever.
Advancements continue to enhance wireless technology. Faster speeds, mobility, convenience, flexibility, and broader coverage are constantly being developed.
Wireless networking has revolutionized how we connect and communicate. It's integral to the fabric of modern technology. Wireless networking offers several advantages over wired connections. Users can access the internet and network resources from anywhere within the coverage area of a wireless network without being tethered to a specific location by cables. Common applications of wireless networking include home Wi-Fi networks, public Wi-Fi hotspots, enterprise wireless networks in offices and campuses, and wireless communication between devices in Internet of Things, IoT deployments.
By combining routing, wireless access, and network management functionality, wireless routers provide a convenient and versatile solution for creating and managing wireless networks in homes, offices, and other environments. Okay, let's keep momentum going. Next, let me introduce you to network architecture.
Picture a vibrant metropolis where information moves as swiftly as traffic, navigating through roads and intersections. That's the essence of computer network architecture. Computer network architecture refers to the design and structure of a computer network, including its components, layout, protocols, and communication mechanisms. It encompasses both the physical and logical aspects of network organization and operation. At the heart of this network city is the router, acting like a traffic controller. It ensures data packets find the quickest and safest route to their destinations. It directs data packets between devices on a network, determining the most efficient path for each packet to reach its destination. By analyzing network addresses and using routing protocols, routers manage and regulate the flow of data traffic within a network, ensuring that packets are delivered accurately and efficiently.
Next, we have switches, which are like the smaller roads that connect different districts within our city. They help direct the data to the correct building, or in this case, the right device. A switch forward data packets between devices within the same local area network, LAN. Unlike routers, which operate at the network layer, layer 3, and make decisions based on IP addresses, switches operate at the data link layer, layer 2, of the OSI model and use MAC addresses to forward traffic. Switches examine the destination MAC address of incoming data packets and forward them only to the appropriate port connected to the destination device. This process reduces network congestion and improves efficiency by minimizing unnecessary data transmission.
Now, consider the cables and Wi-Fi signals as the city's infrastructure. These physical and wireless paths are crucial for carrying the bustling data traffic. Cables provide reliable and high-speed connections for devices requiring stable data transmission, while Wi-Fi offers flexibility and mobility for devices accessing the network wirelessly within a certain range. Depending on the specific requirements of a network and its devices, a combination of both wired and wireless connections may be used to optimize network performance and usability.
Each neighborhood, within the extensive framework of our network city, operates as a local area network, commonly referred to as a LAN. These networks represent the smaller, more intimate connections typically found in residential homes and corporate offices, providing essential links for daily communications and operations.
Then there are the wide area networks, also known as WANs, which are essential for connecting larger areas, such as entire cities or regions, to each other. These networks are capable of spanning vast distances and can even connect different continents, facilitating global communication and data exchange. WANs typically utilize public or private telecommunications infrastructure, such as leased lines, fiber optic cables, or satellite links, to establish connections between geographically dispersed locations.
To ensure the continuous safety and security of our city, we have implemented robust firewalls and stringent security protocols. These systems function similarly to the city's vigilant police force, actively guarding against any data breaches and cyber threats, thereby maintaining the integrity and confidentiality of our digital environment.
In every network city across the globe, there exists a crucial necessity for ongoing upgrades and continuous maintenance efforts. This is imperative to ensure that the transmission of data remains uninterrupted, quick, and efficient, akin to the optimal functioning of a meticulously maintained urban environment. By persistently updating and caring for our digital infrastructure, we can maintain the high standards necessary for seamless connectivity and communication. The power of a network infrastructure. Okay, let's move on. Next, I want to introduce you to network segmentation, where networks are divided into smaller networks, isolated segments, or subnetworks, typically for the purpose of enhancing security, performance, and manageability.
Network segmentation. This process is vital for enhancing the security and performance of a network. Network segmentation involves dividing a computer network into smaller, isolated segments or subnetworks to enhance security, performance, and manageability. Here are some key purposes and benefits of network segmentation.
Enhanced security. Segmenting a network limits the spread of cyber threats across different segments, essentially containing potential breaches to smaller areas. One of the primary purposes of network segmentation is to improve security by isolating sensitive resources and limiting the impact of security breaches or unauthorized access. By dividing the network into segments, organizations can implement access controls, firewalls, and other security measures tailored to the specific requirements of each segment. This helps prevent lateral movement of threats within the network and reduces the attack surface, making it more difficult for attackers to compromise critical assets. Network segmentation also allows for better control over network traffic. Administrators can enforce policies more effectively, tailoring access and security measures to specific needs. Next, consider the performance aspect. By dividing a network into segments, we can reduce congestion. This ensures that critical systems run smoothly without interference from less critical traffic. Isolation of resources. Network segmentation allows organizations to isolate different types of resources or departments within distinct segments. For example, finance, human resources, and research departments may each have their own network segment with restricted access to sensitive data. This isolation helps contain potential security incidents and ensures that resources are only accessible to authorized users. Segregating network traffic into smaller segments can improve overall network performance by reducing congestion and optimizing bandwidth usage. Critical applications or high-demand services can be allocated dedicated network segments with sufficient resources to meet performance requirements. This prevents bandwidth-intensive traffic from interfering with other network activities and ensures consistent performance for users.
Compliance is another crucial benefit. Certain regulations require sensitive data to be separated from other network traffic. Segmentation helps in achieving and maintaining these compliance requirements. Compliance requirements. Many industries have specific regulatory requirements regarding data privacy and security. Network segmentation helps organizations comply with these regulations by implementing controls to protect sensitive data and ensure proper access controls. Segregating sensitive data into isolated segments can simplify compliance audits and demonstrate adherence to regulatory requirements.
It's also about oversight. With network segments, monitoring becomes more manageable. Anomalies and suspicious activities can be detected more quickly and with greater accuracy. Implementing network segmentation isn't just about adding barriers. It's about creating smarter, more efficient pathways for data to travel securely.
Network segmentation is not just a technical strategy. It's a critical component of a holistic security posture. It ensures operational resilience and compliance, safeguarding both data and systems effectively. Simplified management. While network segmentation adds complexity to network infrastructure, it can also simplify network management by breaking down large networks into smaller, more manageable segments. Each segment can be independently configured, monitored, and maintained, allowing administrators to focus on specific areas of the network without impacting the entire infrastructure. This modular approach to network management enhances agility and scalability, particularly in large or distributed organizations. Overall, network segmentation is a critical strategy for enhancing security, improving performance, and meeting regulatory requirements in modern IT environments. By carefully planning and implementing segmentation strategies, organizations can mitigate security risks, optimize resource utilization, and streamline network management processes.
So, next, I want to quickly go over some basic aspects of the wide area network that we discussed previously. By now, we know that the wide area networks, WANs, encompass a variety of components and technologies to facilitate communication over large geographic areas. Some fundamental elements of WANs include routers, switches, modems, communication links, multiplexers, protocols and standards, and virtual private networks, VPNs. VPN, or virtual private network, is the only one we haven't covered. VPNs enable secure communication over public networks by encrypting data traffic and creating secure tunnels between remote locations and the central network. VPNs are commonly used to connect branch offices, remote users, and partner networks to the WAN securely. Okay, let's move on to risk management.
Welcome to our deep dive into network risk management. Today, we're exploring why it's crucial for safeguarding your business's digital frontier. Network risk management involves identifying, assessing, and mitigating potential risks and vulnerabilities within a computer network to minimize the likelihood and impact of security incidents and disruptions. Here's a breakdown of the key components.
Network risk management involves identifying, assessing, and mitigating risks to your network. Each step ensures that potential threats do not turn into actual disruptions. Risk management is an ongoing process that requires continuous monitoring and review. Organizations need to regularly monitor the network for new threats and vulnerabilities, assess the effectiveness of existing controls, and adjust their risk management strategies accordingly. This may involve conducting periodic risk assessments, vulnerability scans, penetration tests, and security audits to ensure that the network remains secure and resilient over time.
First up, we identify risks by analyzing network traffic, monitoring for unusual activity, and staying updated on the latest cybersecurity threats. This proactive approach is key. This step involves identifying and cataloging potential risks and vulnerabilities within the network. Risks can include threats from external sources, for example, hackers, malware, as well as internal factors, for example, misconfigurations, human error. Network assessments, vulnerability scans, and threat intelligence analysis are commonly used techniques to identify risks.
Next, assessing these risks involves understanding their potential impact. This could mean analyzing how a breach could affect business operations or client data security. Once risks are identified, they need to be assessed in terms of their likelihood of occurrence and potential impact on the network and the organization. This involves quantifying risks based on factors such as the severity of vulnerabilities, the value of assets at risk, and the effectiveness of existing controls. Risk assessment methodologies such as qualitative analysis, for example risk matrices, and quantitative analysis, for example risk scoring, can be employed.
Mitigation strategies then come into play. We implement robust security measures like firewalls, antivirus software, and encryption protocols to protect the network.
But it's not just about technology. Training employees on security best practices and maintaining awareness are equally important to fortify defenses.
Regularly updating risk management strategies is crucial as new types of threats emerge. This dynamic approach keeps security measures effective and current.
Network risk management is an ongoing process that requires vigilance and adaptation. It's essential for protecting your assets and ensuring your business thrives in a digital age. Next, let me introduce you to security in network design.
When we talk about security in network design, we're addressing the strategies and technologies used to protect data and maintain integrity within a network. This ensures that information remains confidential and accessible only to authorized users. The implementation of measures to protect the computer network from unauthorized access, data breaches, and other cyber threats. It encompasses various aspects such as access control, implementing mechanisms to control who can access the network resources, including authentication, verifying the identity of users, and authorization, determining what actions users are allowed to perform. The first layer of security is physical. It involves securing the hardware where data is stored and accessed. Protecting network infrastructure such as servers, routers, and switches from physical tampering or unauthorized access by implementing measures such as access controls, surveillance, and secure storage facilities. This can include anything from locking server rooms to using surveillance systems to monitor access points.
Beyond physical, we delve into network security, which protects the data transmitted across the network. Firewalls, antivirus software, and intrusion detection systems are key tools that help monitor and block unauthorized access. Establishing and enforcing policies and procedures governing the use of the network, including password policies, data handling guidelines, and rules for acceptable use.
Encryption is another critical component. It scrambles data so that even if an unauthorized party intercepts it, they cannot interpret it without the correct decryption key. Implementing encryption techniques to secure data as it travels across the network, making it unreadable to unauthorized parties. This includes protocols such as SSL and TLS for securing communication over the internet, and VPNs, virtual private networks, for creating secure tunnels over public networks.
Network design must also consider user authentication processes. Methods like passwords, biometrics, and two-factor authentication ensure that only authorized personnel can access the network. Addressing potential internal threats is essential. This involves setting up permissions and roles to control the level of access each network user has, preventing any single point of failure.
Regularly updating and patching software helps protect against vulnerabilities. Network administrators must stay ahead of potential threats by keeping systems up to date and conducting regular security audits. Keeping network devices and software up to date with the latest security patches and updates will mitigate vulnerabilities that could be exploited by attackers. Educating users and employees about security best practices, common threats, and how to recognize and respond to potential security risks, such as phishing attacks or social engineering tactics.
Lastly, a robust security policy ties all these elements together. It outlines the protocols for handling and protecting data, ensuring all network design decisions align with best practices in security. By incorporating these measures into the design and implementation of a network, organizations can create a secure and resilient infrastructure that reduces the risk of cyber threats and helps safeguard sensitive data and resources. Now, to the last subject in this series, performance and recovery.
We'll delve into the crucial concepts of network performance and recovery. These are key to maintaining efficient digital interactions. Network performance refers to the efficiency and effectiveness with which data is transmitted and received across a computer network. It encompasses several key metrics, including bandwidth, which is the maximum data transfer rate of a network connection, typically measured in bits per second, BPS, or its multiples, Mbps, Gbps. Higher bandwidth allows for faster data transmission.
First, let's define network performance. It involves measuring the quality of service of a network, including its speed, connectivity, and reliability. Network recovery refers to the ability of a network to recover from failures, disruptions, or security incidents and restore normal operations in a timely manner.
Why is this important? Because good network performance ensures that applications run smoothly and data transfers efficiently, which is essential for any business today. The time it takes for data to travel from the source to the destination across the network. Low latency is desirable, especially for real-time applications such as video conferencing and online gaming. The percentage of data packets that fail to reach their destination due to network congestion, errors, or other issues. Minimizing packet loss helps maintain data integrity and reliability.
Now, shifting gears to network recovery. This term relates to a network's ability to maintain or quickly resume function after a problem or failure. Prioritizing certain types of network traffic, for example, voice or video, over others to ensure consistent performance and meet service level agreements. Optimizing network protocols, configurations, and routing algorithms to minimize latency, packet loss, and jitter.
Effective network recovery strategies can dramatically reduce downtime. This is critical as even a few minutes of downtime can lead to significant financial losses. Distributing network traffic across multiple paths or servers to improve performance, scalability, and reliability. How do organizations achieve robust network recovery? Through implementing strong backup solutions, having redundancy plans, and continuous monitoring. Implementing redundant network components, for example, routers, switches, links, and failover mechanisms to ensure high availability and resilience against single points of failure. At the intersection of network performance and recovery, we find network resilience. This is the ability of a network to provide and maintain an acceptable level of service in the face of various faults and challenges. Fault tolerance, designing the network architecture to withstand failures without impacting service availability or performance. Incident response, having an incident response plan in place to detect, contain, and mitigate security incidents and minimize their impact on network operations.
Understanding and improving network performance and recovery is not just about technology, but about safeguarding the core operations of any modern organization. Disaster recovery, developing and implementing plans and procedures to recover from major disasters, for example, natural disasters, cyber attacks, and restore network operations. Backup and restore, regularly backing up critical network configurations, data, and resources, and having procedures in place to quickly restore them in the event of a failure or data loss. And finally, by focusing on both network performance optimization and recovery capabilities, organizations can ensure that their networks deliver high performance, reliability, and resilience to meet the demands of modern business operations. And with that, we conclude the second series on network operation. Stay tuned, for we are working on a global IT portal that will encompass additional areas in IT with a more detailed, hands-on approach. If you're aiming for a career in computer networking, mastering the insights from these series will definitely put you on the right path. Best wishes and goodbye for now.